Welcome back to COMP526. We're in the sorting unit, and in part 3, we'll talk about sorting with many processors using parallel computation. This will also be a theme that goes beyond this sorting topic, but I introduce it in the sorting chapter because it nicely fits there, and it's sorting is a problem that's simple enough to solve sequentially in many ways. And at the same time, it's not completely trivial to do it in parallel. Indeed, depending on how you look at it, it's far from trivial to do it in the best possible way. So I think it's a nice topic to look at from this new angle of parallel computation. So we had this last time already. I think it was 2/3 or so had seen some form of concurrent programming. And I'll give some more general introduction to this because also the terminology might be not completely clear. So first of all, money can buy you love, but also can buy you time, but it can buy you computers. So that's why people love parallelism. You can easily put a big basement full of computers and call it a supercomputer. But the challenge is to make use of these machines because they're different from just having a single processor that runs absurdly much faster. It's not the same thing. You may know these stories about Moore's law, about the number of transistors in integrated circuits doubling every 18 months or so. That has been true for a long time, since, I don't know, the 60s or so-ish. And it seems to be still kind of true, but in 90s, early 2000s, this meant that the speed, the clock speed of processors also doubled with that speed. And so you didn't need to do much to speed up your programs. You just waited for the next generation of CPUs. But these times seem to be over just because of too much heat essentially created in the circuits. So the modern processors still have more transistors, but they use them in a different way. They can't just crank up the clock speed. So instead, we go into the breadth and add more cores to CPUs. That's just for background. I'm probably not telling you much new. You all have devices in your pocket that are probably quad core, 8 cores, whatever. This used to be exotic machines some decades ago, and today you hardly find a machine that is not a multi-core. The Raspberry Pis might be some of the exceptions. I think they have fairly traditional single-core architecture. All right, just for context. If you talk about parallel computation, there's two main fields or realms that you should probably keep separate because they're quite different in the algorithmic solutions that they require. And there's, on the one side, shared memory machines. And on the other side, there's distributed computing. These are abstractions. There's many different forms in each of these. But they're still, I think they're distinctively different in some abstract way that I'll explain to you. I want to stress that we'll focus in this class on the shared memory point of view. And we'll look at it from a fairly abstract machine model so that what you create is portable across different machines. But the algorithms we'll look at, if you just take them as they are, they will not be the best way to do it on a particular machine. There's lots more you have to do to put into this, which unfortunately is often machine dependent to some degree. So we'll try it again to stay in this realm of eternal truths and take the abstraction of the machines we have. What is a shared memory parallel computer? So it has different cores, different processors, and the terminology we'll use here is PEs, processing elements, just to have a separate term that you're not confusing with cores or processors. These are a little ambiguous. In actual hardware, you may have a processor, maybe the chip, and then the chip has several cores. Maybe each core has actually several hardware threads because they're hyper-threaded. So the discussion becomes a bit complicated. And to avoid that, I want to use a new term. And that's also in the textbook that's referenced on the website. So PEs is just the term we'll use for individual things that can execute pieces of code. Okay? And we'll always assume that we have P of those, even though we'll not always need this parameter. Now, if you have different entities that compute, they need some way to communicate. And that's where the two models differ, shared memory and distributed computing. In a shared memory computer, you have one big piece of RAM. Think of it like in the PRAM model, it's one huge array. That will be our abstraction. And this memory is accessible from all the processing elements. So they can all talk about memory address 5000, whatever, some bit pattern, and they will see the same memory. The hardware has to do some tricks to make this efficient. In particular, caches are a complicated topic in parallel computation. But we'll, for today, for this sorting topic, ignore these complications. And this is the only way that the processing elements can communicate. They share this memory, so they can write to specific memory locations certain values, and then another processing element can read from there, and that's how they learn something about the other computation. If you want a typical machine that fits in this topic, think of a big compute server that has several cores. They may have quite a few cores, not thousands, but hundreds, and they can have really big shared memory. So this would be expensive to buy a terabyte of main memory, but it's not technically infeasible. The other model of parallel computation that we will not talk about in this module much, but I want to mention that MPI is more in this context, and this would be more OpenMP if you want to contrast those two. And also like the Java concurrent framework, so say Java threads, same C++ threads and Python. All the things that tend to be built into a programming language, they tend more to be on the shared memory side. Even though sometimes they abstract even further, and then the two models are maybe not so distinct anymore. We'll see more concrete examples. Okay, what's a distributed computing? What's the difference? We again have processing elements, but they have private memory, which is only visible to them. And if they want to communicate, they have to explicitly send messages. And MPI is one way to do that, where it's sort of transparent if these are different operating system processes running on one machine or if they're communicating over a network. Usually you'll assume for these messages that each processing element has an ID, a number. And pardon? Well, semaphores are, that's a different way. We'll talk less about this. You'll see in a second why. Semaphores are a way to manage synchronization between different processing elements. On the distributed computing model, what you will assume is that the messages kind of synchronize the processing elements. In the simplest way, processing element I says, I want to send a message to processing element J over here. And so it waits until that guy has acknowledged the receipt of that message. And that's a way how they can synchronize their communication, their computation, by having this one wait for the other to acknowledge, yes, I received it and I'm at the same spot now. That's one way of synchronization. You may guess that waiting for the answer might not always be the best thing, but that's the simplest and is actually often quite powerful. In terms of concrete hardware that fits into this model, think more of a cluster of machines that are connected through some Ethernet or some more dedicated network. You will have heard of supercomputers, which are, interestingly, somewhat a combination of the two. They tend to have a cluster because you can't build a single machine and scale it up that much. But each of these elements, I shouldn't say little, consists of one of these servers, maybe not quite as big, but definitely with several cores per node. So a supercomputer is combining the two models, and that makes programming them sometimes a bit more challenging. We'll concentrate on the first model, which also means we'll concentrate on problems where the entire data you're working on fits into one compute node. But again, terabytes of main memory is not a fantasy, so this is not much of a restriction. It's more a question of how much money do you want to put into the machine, or do you have to work on an existing cluster? Now, these are the models for the two big, paradigms. And I talked a bit about hardware that we actually have. But what I want you to work on for the algorithms is even more abstract. And that's the parallel RAM machine. So parallel random access machine model. For short, PRAM. You will remember from Unit 1, hopefully, unless you forgot, in which case you can go back to the videos, what the RAM model is like. It was, in short, it was one big array of integers, essentially as long as you need it. And each integer was a certain size, W bits, and then you could fetch a cell, store a cell, compute internally. That's pretty much what you can do, and have conditional branches. Now for the PRAM, you have P of these RAM machines, but they share the memory. So the memory is shared among all the processing elements. It's a shared memory computer, remember. And another important thing is all the processing elements run a RAM program, but it's actually the same for each, where we just use the ID of the processing element as a variable inside the program. So they can do different things. They can depending on what their ID is, they can go into the one end or the other end of the code. But the pseudocode we'll write down will be valid for all processing elements. That makes it easy to write it down. And then each processing element, depending on its ID, may do different things. And now the last big step, last big part of this model that makes programming it much easier is these P processing elements all run in lockstep. They have globally synchronized time steps, and they all execute one instruction, then they wait for everyone, and then they do the next instruction. Now that's the biggest criticism people have for this model, because this is not what hardware can really do. In hardware that we have, multi-core processors, the different cores, they run at not necessarily at different clock speeds, but they run at a different number of instructions per second for sure, because the instructions take different times. And especially you can have instructions that access memory that have to wait for caches. So the time is not just the same time for each instruction. And so they get out of sync. So much of the work that you have to do after the abstract algorithm has to do with getting the synchronization fast on the existing machines. And it's maybe fair to say that this is still active research how to best do this. There's been a lot of advances to make this a little less cumbersome. What we'll touch on here is just the basic underlying part that is more settled, I would say. So we'll just assume that all the processors do one step at a time, and we don't have to bother about synchronizing them. Now you can simulate this on an actual machine by explicitly synchronizing using something like semaphores. It would be a slowdown, so it's maybe not the best possible way, but it's definitely implementable. This is not completely esoteric. It's just not the most efficient way on the existing machines we have. Okay, is the model clear so far? So P-dependent RAMs, they all execute the same program and they run in lockstep. Now, if you think about this for a moment, you have different processors. They all happily compute things. They have their own sets of registers, right? These are separate. They don't see each other's registers for computing. But if they load and store to the shared memory, they hopefully see what the other processors do, because that's the whole point of shared memory. But what if in the same time step, several processors want to write to the same location? They might overwrite each other's values, or they might create a conflict, and we have to do something about this. So that's what this slide is about. We have to somehow define in the model what should happen if more than one processor writes to one specific location in memory. And you can come up with different solutions. One would be you completely forbid this. The EREW PRAM says all reads and all writes of all the processors have to go to different locations. If your program doesn't ensure this, it will the machine will explode or whatever. I mean, it crashes with some error. It's not allowed. Your program is not, wouldn't compile or something like this. It would throw an error. That's one option. This is very restrictive, but sometimes this is enough. What's definitely slightly more general and works just as well is to allow concurrent reads, because reading the same location at least is well defined. They will all retrieve the same value. So there's no problem on that side. And indeed, this is something that hardware supports. Reading a value from shared memory is fine if this is done in parallel. There's not a substantial slowdown from doing this. And in this model, still, writes have to be exclusive. So only one processing element can write any cell at any time. A more general model allows concurrent writes, but then you have to say what should happen. And there's, again, different ways how you can resolve these conflicts. An interesting one that might be a bit weird at first. You allow concurrent writes, but if they happen, they all have to write the same value. So there's no conflict, really. It's just the processing elements don't know about this, but you as a programmer can make sure from the outside that if several write to the same location, they will always write the same value. We'll see an example in the tutorials for this weird model, why this can make sense. The other one is maybe more like what hardware builders would like. You can write several values to the same location, but then arbitrary things can happen. Any of those values wins, and you don't get a guarantee which one. There are other things that would happen, that could happen. You can come up with different models, and in a sense, it's not completely fixed what the hardware will do. There have been different approaches tried, and so this is still somewhat ongoing. That's why we have this wealth of different models, just to make to play with the possibilities that they give us. The default model here, though, will be the crew PRAM. So we allow concurrent reads, but we don't allow concurrent writes. That avoids the main bottleneck that PRAM algorithms see in practice, apart from the synchronization. Namely, if several processing elements write to the same location, you get into something in actual machines called cache coherence problems, and then there's cache coherence protocols. Just as an aside, like this is not in this model, but suppose one processor writes to a certain memory location. It actually doesn't write to main memory. It writes to its local copy in its own cache. If this other processor wants to write the same location, then these caches contradict, and so they somehow have to be reconciled that they reflect the same value. And that means they have to talk to each other, and that's slow. So in a way, writing to the same location is something that will inevitably slow down your concurrent programs. And there's essentially nothing I know of that hardware can do really about this. There's ways to make this not get completely arbitrary behavior, but they all have a slowdown. So it's not only a nice model to look at because it allows interesting algorithms, it's also one that encourages you to do things that will run fast by only allowing one write access per memory location. Okay. Okay, good so far? There's one last thing about the model. we have to tell, if we want to analyze algorithms, how expensive are different things. And as before, there's different cost metrics that we could look at. Space and time are the same as before, so not really surprising. But we'll have to talk about time in a second a bit more. Space is easy in the PRAM model because we have this shared memory. We'll only look at how much shared memory we'll use. So that's same as in standard RAM. For time, in PRAM, there's a well-defined time, namely the number of time steps that the program runs. Now, notice that not all processing elements are necessarily still active till the last time step. They all execute the same program, but they have their ID. That means they can go to different branches. So they might go to sleep or basically terminate ahead of time, whereas some other processing element might still be running. So by time, we mean the number of time steps till all of them have finished. You will see this called either the parallel time or the depth or the span of an algorithm. All are really talking about the same thing. And here, maybe this doesn't really deserve to be in small print. We will usually assume for the analysis that we have as many processors as we like. Again, not a reasonable assumption in practice, but I'll come back to this in a second. It is a reasonable assumption for the analysis. Why we do this in short, we want to see what is the limit of parallelizability in this algorithm, and not what's the limit of the machine we're looking at. So we give it as many processors as it can sensibly use and see if that helps to bring the parallel time down. Okay? And a second important parameter is the total number of instructions executed across all the P processing elements. So in this sense, for work, in work you pay for using many processors, because the time is in a sense multiplied with the number of processing elements. And then the goal of designing PRAM algorithms is to minimize the time, as usual in our goal in algorithmics. But we also want to minimize the work. So the ultimate goal would be have a parallel algorithm with minimal parallel time or minimal span, and the work not much worse than the best sequential algorithm. Okay? And this is what we call work efficient. So the work of the parallel algorithm is big theta of the work, the time of the best sequential algorithm we know of. All right, time to wake you up. Simple question, just drilling on this definition. Now, let's see if Slido works again for everyone. We've got quite a few votes for the last question, so I'm somewhat confident. Hopeful, say. And you guys read the question very carefully. Give you a few more seconds. We're at 49 on the last question. I say it's 3, 2, 1, and locked. All right, so it seems the majority is convinced. And wrong. I don't enjoy this as much as it sounded. But let me explain why you were wrong. It's probably how I posed the question, partly. The question is, does every computational problem allow a work-efficient algorithm? It doesn't say that this has to be a good parallel algorithm. it could be a crappy parallel algorithm that just runs on one processing element and does exactly what the best sequential algorithm would have done. In other words, it is the best sequential algorithm, just not making use of parallelism. And so it's by definition work efficient. So you can always do this, but in an uninteresting way, right? So you can always achieve work efficiency, but this is not by itself interesting. Interesting is the combination good span and work efficient. But why care about work at all? I mean, we care about time, and we can buy a few more processors, so why bother about work? This is not really time that we spend. The thing where it becomes important is not where I want it. Where it becomes important is the observation that you don't usually have theta of n processors. If, say, you're sorting a list of 10 million integers, you don't have 10 million cores, no way. And even if you had, maybe this is not how you want to use them. So these notions of span and work seem a bit, well, in a negative sense, academic. I want to convince you that they're not as useless as they may seem at first sight. And this is what's known as Brents' theorem. If you have any parallel algorithm that has a given span, t, and a given work, w, where, I mean, here the work and the span assume that you have as many processors as you want, then you can actually run this on a what is this doing? You can actually execute this on a PRAM with p processing elements. So if you have your concrete machine, you can insert what p is, and you can work out that the parallel time comes down to this. It is the span of the original algorithm, but plus w divided by p. And you're still using essentially the same work up to a constant factor more. So why is this important? It means if we have for some parallel algorithm with this unrealistic assumption, arbitrarily many processors, if we have analyzed the work and the span, we can go to a concrete machine with a given number of processors and compute what is the time and work on that machine. Okay? And the way to do this, at least in theory, is very easy. As this is one-line proof, but maybe a little example is useful. You just schedule the steps that the algorithm would do on arbitrarily many processors, round robin across the p processing elements you have. So maybe in the interest of time, let me do a smaller example. Suppose the original uses 6 processing elements. And so time proceeds top down. The first time step, they all do something. They execute one instruction. And then in the next time step, they do another instruction. Remember, they're all nicely working in lockstep. They proceed through this at the same time. And maybe the algorithm is really fast. It gets the job done in 3 time steps. So that would mean t is 3 here, and work is, well, if we just sum up all those, we get to 18, assuming there's no other overhead. Now, how could we simulate this on, say, 4 processors if we don't have 6? We would take, in the first time step, we would get these 4 scheduled. In the next time step, we take, these are actually 7. So 7 times 3 is not 18. So in the second time step, we have 3 left. So these are these first ones. For the first 4 processing elements, what they do in time step 1. If we simulate it on 4 processing elements, we have to do another round of these. That's the remaining 3. Okay, so we need 2 time steps. Then the same thing happens for the red ones. And maybe I should have cut the example short. This is probably easy enough for you to imagine how this continues. We can make it slightly more interesting by saying a few of these actually finish early. So we don't have the full. But we do the same thing. We take the first 4 that we have, and there's one more that has to go in a second time step. So you can work out what time and span on the 4 processing element PRAM would be then. And if you think about this in general, if you have to simulate here these what could I call these, M steps that we do, you need M divided by P time steps each. Now we just need a bound on M. So here we used M processing elements on this side instead of the P that we have. And we can use the work and time to get to this. So the work is M times the time. So we can solve for M. And then what do we need here for one of these simulation steps? We need M divided by P. And if you insert what M is, that happens to be T divided by PW. And now we don't have this just once, we have this T time steps. Did I somehow mess this up? That it doesn't. Yeah, okay, solving equations is a tough one. You should have told me. What's the use of you being here if you don't tell me I'm doing nonsense? Okay, so we have that number of steps for each little execution step. And we have T of these steps, right? So the total time for the simulation is T times this one. If we want to be precise, we have to round this up. So it's T times W divided P times T rounded up. And now I wish I had a little more space. Wish granted. So you can upper bound the rounding up by +1, right? So you can multiply this out, then you get W divided P plus 1 times T. And that's exactly the bound that we get here. You can analyze the work as well. The work, we're doing this roughly the same number of steps, right? There's maybe a little overhead for simulating this that I didn't show on the slides. Is the concept kind of clear? So what does round-robin simulation mean? You just take from left to right the next available job. It's a general way of scheduling jobs. Here we do it on very tiny little jobs. It's one operation of one PRAM processing element. So we probably don't want to do it at this small scale, but the same idea on a more coarser scale with bigger tasks does work well. Okay, so much for the PRAM model. Question? Yeah, it doesn't make a big difference. You're right. Round robin is one solution. So the question was, why do we take round robin scheduling here instead of something simpler like first come, first serve? You have to make sure that you first execute everything from the black portion, the first time step in the original program, get all those finished, then wait, and then start with the red ones. Because remember, these black ones, these black instructions could be write something to memory. So we want this to be finished before we continue with the red one, which could be read that memory from a different processing element.